Welcome back to class number 9, where we are dealing with internal energy, and we're going to work a little bit on this example. Determine the missing property, P, T, or X, and V, which is specific volume, for water at each of the following states. So we have a temperature at 300 degrees Celsius, internal energy at 2,780 kilojoules per kilogram, and then we also have 2,000 kilopascals and internal energy of 2,000 kilojoules per kilogram. And here's already the answers down here, or close to it, right in there. So just we'll come back to that after we take a look at the examples here. All right, so let's take a look at table B 1.1. It's always a good place to start when it comes to water. Not always. Sometimes B 1.2 if we were given pressure. But for here, for part A right here, at T equals 300 degrees Celsius, we will find a PSAT from that table. I'm hungry. I'll go home and eat. I haven't had dinner with my wife in a couple days. So I want, let's see, what did we say? 300 degrees. That's not on this table. Flipping them over. 300. That's the pressure entry. No, here we go. Okay. So here you go. 300 degrees. Let's see if we can get 300 degrees. Boom, boom, boom. We get 8,581. All right. So I'll go 8,581. 8,581. That's a lot. But let's see if we want, first thing we want to do is see if this thing, that falls in the range of this. And we take a look over here to internal energy. And what were we given for internal energy? 2,780. All right, so you look over at this far right column. You got to look at the top, and this is the saturated vapor. And I got to make sure we get it there. Here's the 300. Our 2,780 is larger than this. Therefore, we must be superheated. Right? Here's the logic we have to keep going here. So UG is equal to 2,563 kilojoules per kilogram, which is smaller than our U, therefore superheated. So let's go to, for this part A, table B.1.3, the superheated table. Now those are going to be arranged by pressure, so we're going to have to jump around and look for these pretty carefully. I kind of already know what the answer is, so let's see if I can find. Well, okay, so we got to, here's B.1.3. We have to look for all of the 300 degrees Celsius ones. Right, so let's just randomly pick one right here. So here is our internal energy at 300. We have 2,789. Wow, wait a minute, that's really close. 2,780 is what we had. All right, so let's see what, and for our pressure, let's see what we have over here. We have 2,785. All right, so we're still, that's still larger than us. We wanted 2,780, so that's big, too big, that's too big. Let's go down to the next pressure up. We have for 300, 2,781, still too much. And then over here, 2,776. So this is less, right? So we're in between these two is what we've learned. Our pressure must be somewhere between 1,600 and 1,800. So we need to do an interpolation for this to find what the pressure that's in between these two things. So we'll say, I guess I want to document this. So at P is equal to 1600 kPa, and T is equal to 300 degrees Celsius, we get U. I could give it a number. I go with 1600 like that. Is equal to 2,781.03 kilojoules per kilogram, and at P is equal to 1,800 kilopascals, and temperature equal to 300 degrees Celsius. We have U 1,800 is equal to 2,776.83. Crazy amount of sig figs going on here, but let's do it anyway, because it's very slight changes in between here is going to affect what this pressure is. So if we're trying to estimate a pressure based on this information, we're going to be pretty careful. So here's my interpolation right here. I'll set it up here. Here's the thing I want to know is the pressure. We're going above it is this, below it is this. Here's the stuff I know. 2781.03, 2776.8. I don't think it's 83, it's a 03. And then we had this 2,780. 2,780. So remember, we're going to go like that right there. Compare the top to this, divide it by this, the top to there. Compare these, divide by that. All right. So we go 2781.03 minus 2780 divided by 2781.03 minus 2776.83. I keep thinking, I think I keep saying 83 and I mean 03. I'm tired. All right. So we got 1600 minus P divided by 1600 minus 1800. And if you work out through the math from this, you get 1,649 kilopascals, which is what we would want to find. Now, what you'd also need to do, all right, so they said also the V for water, and I didn't do this, but we could, we'd have to interpolate again. And I wish I had written this thing up here, so maybe I could go V at 1600 is this, and maybe V at 1800 is that, and so V at 1600 is 0.21382. These are cubic meters per kilogram. Can't really read that. Okay, yeah, maybe you can. And then for the 1800 is 0.18228. And once again, I wish I had thought of this ahead of time. All right, so what we'll come down to here is probably the easiest way to go is to go with the pressure instead of to go with the internal energy. You could do it either way to find the unknown specific volume. I think it's going to be easier with the pressure, although there could be some mathematical errors because there's some errors that happen here. So I'm going to go with the pressure because it's just going to be an easier number. So I'm going to go this right here and go to V, that's the one that I want. And over here, I'm going to go 1600, and here's 1800, and here's my 1,649. Up above is 0.21382, and here is 0.18228. So do the same thing again. 1600 minus 1649 divided by 1600, excuse me. That's supposed to be a 16. And that's supposed to be a 0. Look how pathetic that 0 is. Damn. What the hell? All right, and then over here, 0.21382 minus, there's the parameter we want, 0.21382 minus 0.18228. Always got to be careful with these signs and that kind of thing when doing this. So, like I said, I haven't actually calculated this out. 1/1600 minus 1649 divided by 1600 divided by 1800. Not divided by minus. Boom, and now divided. All right. So anyway, this was like 24.5, which was what that should have been up there, right? We're just taking the percentage of that thing versus that thing. We're going to multiply this by 0.21382 minus 0.18228. Boom, right? There's the range. All right, so we have a positive number over here, and we're going to subtract this out, and that's going to be negative. Okay, so 0.21382, subtract it out. It is a negative number, so it's going to be, all right, so we have a V of 0.20609, right? But I don't know, we probably had this, there's a round off right here, so that's going to really affect this over here. So that's going to be cubic meters per kilogram. So what we've established for this is we have the temperature and internal energy. X is going to be undecided, but we have the pressure now. From this, we found the pressure and the specific volume from these two pieces of information. It's a very common type of thing once you know two pieces of information. We're also going to be later on, we're also going to get the enthalpy and the entropy in the same exact way. So this is like a useful exercise. Let's go to part B. So this was part A, both of those things. And I should really summarize those here at the end, but I'm not going to. So now let's go with 2,000 kilopascals and 2,000. So that's easy, 2,000 and 2,000. And let's try to look all these things up. So we're going to start off with, let's see, I'll draw a line right here. Table. Well, let's take a look first at table B1.1 and see if we can use it. This is the temperature-based one, but let's see. Here's the pressures. They don't go to 2,000 there. Let's go to this next one. And we could probably use it if we could find... Nope. I think I just messed that up. We're going to go here. Temperature... Okay, yeah, I just need that page. All right. Boom. We're kind of right in there. We can see that we can make a judgment call based on this right here. But luckily for us, we don't have to do that because we have a whole other set of tables, which is this one right here. So that's going to be a lot easier. And that only goes to 800. So let's go to the next page. And sure enough, we got 2,000. 2,000, and we're looking for internal energy right in here. And so let's go to the gas part of this. So over here, boom. Ooh, our internal energy is lower than the saturated vapor. And it's higher than the saturated liquid. It's between these two. Therefore, it must be a mix. So we want to write this stuff down. Right? So, fortunately, I have it written on another piece of paper. So we go at B, 0.1, 0.2, at P is equal to 2,000 kPa. We find the saturated temperature, so that's actually one of the things we wanted to get here was the saturated temperature, so that's going to be a known now, 212.42 degrees Celsius. Very specific. Let's see, I got to write all these down. I think I wrote something down wrong on my sheet, so I'm going to correct it right now so I don't accidentally write it on the board. I had enough time trying to pay attention to shit without writing it down wrong. So 906.42. These are kilojoules per kilogram. UFG is useful to us, so 1693.8 looks like a 4. Kilojoules per kilogram. And then this one, we're just writing it down. to document that 2600.26 kilojoules per kilogram. And so UG is greater than U, therefore it's a mix. Mix. Can't spell the word mix. That's great. So let's find, based on this, we have, we're going to use U is equal to UF plus X times UFG to find X. So we get 2,000. It's going to be equal to 906.42. Right? Okay, right there. Plus X times 1,693.84. And now X, which is the quality, we will find to be 64.56%. Great. But now, so that's one of the things we wanted to find. Here's one of the things we wanted to find. The last thing to find is the specific volume. So we look up for this right here from the table. For 2,000, we have 0.001177. That's a lot easier. 001177. And then we have the FG, the VFG of 0.09845. So write that down. Write that down before we forget. I just forgot. Where did you go? There you go. 001177 cubic meters per kilogram. And then VFG is 0.09845. 845 cubic meters per kilogram. And so V is going to be equal to VF plus X. And I did all that so I can get that X, so I can multiply by this. And so we go 0.001177 plus 0.6456 times, where are you? 0.09845. And we get a V, specific volume, 0.6456 times 0.09845 times 0.001177 plus, and we end up with a 0.06474 cubic meters per kilogram. Boom, boom. And so that's our part B. We were able to answer all of these things, these unknowns, given two parameters. We're given, I guess I didn't write it down right here. We were given this and given that, and we were able to find these others. We're also going to be able to find the enthalpy and the entropy in the same way. And this is an important skill set and mindset, that all of these properties, like if we find two properties, almost always, but pretty much always, if you know two properties, you can find all the others. The exception would be if the two properties were saturation temperature, was the pressure and the corresponding saturation temperature. Those would not be enough information. You'd also need to know what the quality was, because you know that there was a wide range of things that happened in between there. But it'd be very rare for someone to give you both of those things. I suppose it gets, in the real world, it's easy to measure temperature and it's easy to measure pressure. So if you happen to have them saturated and they were like, the gauges were right there next to each other, and you're looking at the thing, you would not have enough information to judge what the full information of the state, because you would be stuck. But except for that scenario, most of the time, two pieces of information are enough to fully establish what the state is.